All right, so hi everyone, welcome again to the Quantum BV Colloquium. I'm Jean Brav from the quantum computing team at Fraunhofer IO, and I'll be guiding you through today's colloquium. So, as the introduction, Quantum BV is the state initiative for quantum activities in Baden-Württemberg to pull all these competencies related to quantum and to create an overarching umbrella that further strengthens these networks and makes them more visible. So with this colloquium, we want to further promote the scientific exchange on quantum hardware and also algorithmic topics in the field of quantum computing, and to present the latest developments in this research area and to promote the idea of co-development of quantum solutions. So today I have the honor of introducing our speaker, Dr. Michael Marthaler from HQS Quantum Simulations. So, little biopic. He has worked in the field of quantum computing for more than 15 years, received his PhD from the Karlsruhe Institute of Technology, KIT, in 2009, and as a postdoc, he worked at the KIT, AIST in Tsukuba, Japan, and at the Saarland University in the group of Professor Frank Wilhelm. And in 2017, he co-founded finally HQS Quantum Simulations. So, good to have you here. His talk will be on quantum computing use cases, optimization, and nuclear magnetic resonance. So in this talk, we'll explore use cases for quantum computers and fundamentally how we even identify use cases to begin with. He will examine why a large part of use case research is guided by complexity theory and how this affects popular use case topics like combinatorial optimization. And also, we'll discuss the role of quantum computing in improving the interpretation of NMR data, aiding the characterization of molecular structures. So, questions can be posted in the YouTube chat. And with that said, I'll hand over the floor to you.
Yeah, thanks. So yeah, it's great to be here. I have a lot of interaction with the Fraunhofer institutes, and I'm happy to be here and give a presentation. And a couple of words. So I'm the CEO of HQS, and HQS was founded in 2017, as mentioned before, and we started to work, with companies like BASF and Bosch on projects in the field of quantum computing. And today we still do this type of project consulting. And in general, our own software development is strongly focused on spectroscopy, which is a strong topic for quantum simulation, and I will discuss this quite extensively during my presentation. And generally what I thought is I just structured this talk about what is a good way to work on use cases, and if we look at our use case, what should the quantum computer do? And if we look at it, how do we see, does that make sense? Will this be long-term, be viable, and so on? And there are 4 obvious points that one can look at, or should look at. And it should be a problem that somebody cares about. And you can look at it, this is really important. And you should have a way to get the problem, and as people, who want to solve it, actually would define it, do you have a way to get it to the quantum computer, into the right form? Then you should also think a little bit about what is actually the way to solve it on a classical computer. And at the end, you need to convince yourself that you can achieve quantum advantage, that the quantum computer can really be substantially faster than a classical computer at some point. And I think the fact that it should be a problem, and since we work on a quantum computer, that we would like the quantum computer to perform well, is kind of obvious. And so I also want to highlight these other 2 points, because actually they can play a significant role and often are somewhat neglected in the importance or in the amount of work that people put into it. Which kind of makes sense, if you want to work on quantum computing, you want to work on quantum computing and not on the classical computing side of things. But I feel this can also produce a lot of value, and it's also necessary for us to understand what is a good idea for quantum computing. And if you look at this, of course, in the end of the day, we often cannot yet show that quantum advantage, not often. So far, nobody has shown quantum advantage for a really practical use case. So we have to have always, when we look at the problem, have to convince ourselves that there is some direction we go to that will lead down the line to the quantum advantage, and that normally means that at least in the direction, even if we kind of heuristically change things a little bit in the direction, it should be guided by algorithms with provable speedup. And then, of course, it also goes the other way around. You look through the list of algorithms that exists and look back, okay, what is actually a good problem that could fit? Yeah, so this goes always a little bit back and forth in practice. And a reason I thought I structured this talk like this, and I feel it's important to consider this a little bit systematic, is because hardware, everybody who works on quantum computing use case, of course, you would love the hardware to be even better. Yeah? It can always be better. But it has made substantial progress. So I think really things are progressing. And if we now look at the future, especially for academic work, you can look into the future 10, 15 years, yeah, and ask yourself, do we really have the smashing use cases that fully justify the billions of dollars that we need to build the error-corrected quantum computer? And I would say kinda, but things could be stronger. Yeah, I think there is really need to make this tighter, such that at the very least for the long range kind of vision of 10, 15 years, we can be absolutely certain that we have really smashing use cases. And if you look at this and do this process where you start from looking through the algorithms and look, okay, what kind of industry problem or problem, generally a super interesting problem can be solved. You could, for example, check the famous quantum algorithm. So then you go through this and look at algorithms, only at algorithms that have more than quadratic speedup. And people who saw this talk, I've given this before, actually might notice that I relaxed it a little bit. I had, in this first point, always choose exponential speedup. So now I relax a little bit, let's say more than quadratic speedup. And I cite here a paper where people discuss this, why we should focus on algorithms with more than quadratic speedup. And generally, this just comes from the fact that quantum computers, when it comes to the takt frequency, or the amount of measurements per time I can do, are actually slow. Yeah? And that's why our scaling advantage has to be significant. It cannot be a minor scaling advantage, it has to be a significant scaling advantage. Fortunately, already a kind of a quadratic advantage is absolutely sufficient. So if you have an algorithm with a quadratic advantage, it doesn't need to be exponential, that's pretty good. But yeah, so you go through the quantum algorithm, so throw everything out with only quadratic speedup, then throw everything out that is only heuristic. Then you remove all the algorithms that need an oracle, that need quantum memory, meaning that needs exponential time to construct. And then you remove all algorithms that are only relevant for cryptography. And then you notice, basically, what remains is HHL and phase estimation things for quantum simulation. Well, up to very recently, that was basically it. Fortunately, things have improved quite a bit in the last year, basically. And for HHL, also people have started, also very, very recently, to construct these oracles successfully. Also super important to actually show that this actually works. And so I think progress is being made, but I think there is a lot of work to be done to make this tighter. And in that spirit, I want to discuss some examples for use cases, namely around this topic of optimization, which is something that a lot of people work on and is very well liked for obvious reasons. Then I want to go through a full use case where we go through all these 4 points that I mentioned in a certain order, that makes sense, to see how this works if you really work deep into a single use case. But let me start with these examples around optimization. And what is, I think, really nice is that people have started to really find combinatorial optimization algorithms with a provable speedup. So if you look at this whole topic of optimization, Combinatorial optimization is a topic that can be found almost everywhere. You know, always a typical problem is like scheduling to make train schedules, or financial portfolio optimization, or all types of things. So it's obviously a problem that if you could solve it super fast, valuable. Therefore, makes sense to look at it. However, I would say the speed up situation was pretty suboptimal, since I would say this was always driven from the wish to solve important problems and less from the question, do we really have a reason to believe that the quantum computer can do it? But very recently, people published, I think it's a team at Google, published a quite interesting paper in which they showed that they can achieve an exponential speed up for a problem called optimal polynomial intersection. It's a combinatorial optimization problem. Fortunately, in the paper, they provide a figure, which I show here, because otherwise I would not, it would be challenging for me to fully understand and or explain the problem actually that is being solved. But the type of problem that is being solved is where you have these areas that are shown here in orange, and you want to put a polynomial through all these areas and touch as many of these areas as possible. So that is the optimal polynomial intersection. Of course, then you can go to any dimensionality in the area and in the polynomial. So this is done in 2D here, but you could go to higher dimensions, making this difficult. And now you might ask, okay, if this is an NP-hard optimization problem, how can you achieve exponential advantage? Because we know that should be impossible. So obviously they don't show this speed up for the exact solution, but they do what is known as an approximation ratio. So they show that the quantum computer can achieve an approximation ratio of 0.7179, which is better than any classical solution. So they can get, with guarantees in polynomial time, closer to the exact solution than any other known algorithm. And that's pretty interesting. Now, so far, and also mentioned in the paper itself, there is no real use case for optimal polynomial intersection. This is a fully abstract NP-hard problem. But this is why I mentioned this. I think it makes it particularly interesting to think about, you know, can you take your traveling salesman problem and transform it into optimal polynomial intersection, which should be possible in polynomial time? And does this preserve the speed up? Which also would require you to know a good solver and good methods to solve the traveling salesman problem, the original problem classically. Yeah? So now possibilities exist to study optimization problems based on kind of provable algorithms, simply by looking, this is an actual use case that people have. It has a mathematical formulation. Can I transform it into this optimal polynomial intersection? And would solving the original problem not have a better approximation ratio than I would later have in this after this transformation? And so I think this is a very, very positive development. And now I want to come to a comment on a lot of work that has been done on heuristic optimization and QAOA. So there are kind of a lot of attempts to basically simply apply, you start with an initial state on your quantum computer that more or less just is the superposition of all possible bit strings of your qubits, which you can trivially generate by just applying Hadamard gates to each qubit. And then you apply unitary operations that will generate some phase that depends on your state. And then if you do this in the right fashion, maybe motivated by adiabatic time evolution or something, or motivated by the Grover algorithm, you hope that in the end you would unwanted states disappear and you retain the solution. And if we say this is motivated by Grover's algorithm, then we can look a little bit and ask ourselves how probable is this that this will work, and we can, for example, or that this will produce positive outcomes. And we can, for example, look at this for a famous problem that is often discussed in the space, the traveling salesman problem, where you have a certain amount of cities and you want to have the shortest path. And if you classically just would use a computer and look through every possible path and ask yourself how long will this take, then you have to look through n faculty paths for n cities. So that's a really badly scaling problem. And then Grover would roughly tell us that the quantum computer should solve it in square root n faculty, which is still kind of a poor scaling and actually worse than the best classical solution, that is n squared 2 to the n. So I mean, you do not have to use brute force on a classical computer. You can do better solutions. So actually, I would say there would be a need to really solidify your arguments if you do a heuristic method, why you believe that you can achieve any speed up to begin with. Now, I recently actually found that there has been a paper that proves to some extent an actual algorithm that beats the best classical one. So that's nice, but actually this algorithm has again nothing to do with any of the heuristic methods. It's far away, it's super complicated. And as you notice, the speed up is actually less than quadratic. So we're talking a less than quadratic speed up for this type of problem, which would be really challenging to achieve a practical advantage given the takt frequencies of quantum computers. So what I would say is, in this field especially when you work on heuristic, I would also always recommend to really think about these first two steps, getting your industry problem into the right form, for example, as a really big thing, or also really considering strongly how would you solve it classically, because this, of course, can produce a lot of value instantaneously if you have really good classical methods. And on the quantum computing side, to really think more abstract on provable topics or on really well-motivated issues. So don't even orient it maybe too much already towards the industry use case, but more the need to make fundamental arguments why it will work. And with this, I move on to the NMR use case on which we work at HKS a lot. And since I know, people, I think that's the way I prepared the talk, have a technical background here, and I'm probably not specialist in NMR. Let me say a couple of words on what NMR is and what it does. So in NMR, you have a device that looks like this. Very often it's like from poker. What you do there is you put like a vial, for example, of a substance. We have dissolved a complex molecule in some liquid, and put it into this machine. Then this machine applies a very big magnetic field. This is why it's so big, because it needs superconducting magnets. And then you shine microwaves at your liquid, and then get back some microwaves, which you frequency resolve, and then you get like in frequencies something that looks like what I show here. And yes, the frequency is accounted in ppm. That is the frequency measure used by chemists. I, of course, would prefer hertz, but actually ppm makes sense in the context of chemistry, so let's just accept it. And now what do you see here? So the magnetic field is actually responsible. So what you see is the response of the nuclear spins, so nuclear magnetic resonance, so you need the nuclear spins, and their frequencies have been moved apart by the magnetic field. So then you see very nicely resolved signals, although even with strong magnetic fields, they are not always super nicely resolved. And now what you can do is say, okay, I see a peak at this particular frequency. This I know must be a proton, because I look at protons. And the fact that the frequency is there means that there is kind of a shift coming from some other part of a molecule. Now that shifts the frequency of the spin. And now you look at the other peak, and again you say, okay, this must be some other part. And then you go through all these peaks, and then you see, okay, this is what should be there. And now I'll put this all together, and then I would know that this spectrum is spintool. And now, this is possible. That's why people do it during this assignment, going through the spectrum and looking at it and finding out what molecule you have. But actually, it is quite annoying and can take quite some time. And if you want to make sure, often it's done even by two people independently to check that it's done right and so on. So it's quite an extensive thing. So having a really nice way of saying, this is my molecule, what is the spectrum, would be very nice. Of course, even cooler would be the other way around. But even going from molecule to spectrum in a reliable fashion would be quite nice feature. And so this is something that, this NMR spectroscopy is done at every pharma company every day. So it's a quite common problem. And therefore we have a really nice problem here. And now I want to directly jump to this point, why quantum advantage? So what does it have to do with quantum computing? In some sense, of course, I think for people here, immediately understand molecules, quantum mechanics, quantum simulation, somehow that's all related. And so there are obvious reasons why we believe this problem can achieve quantum advantage. But let me motivate this a little bit more. Of course, it starts from the fact that the object of nuclear magnetic resonance is a spin, while the qubits are also spins. So this directly maps really nicely to each other. It's a little nicer than if you have problems that have fermions, which you have in ab initio quantum chemistry. And you see this actually also when you look at algorithms. In algorithms, you can much quicker, for example, let's say if you have a kind of a processor, like an actual layout of your qubits, of let's say physical qubits, and you have your spin problem and want to map it, like your spin problem to your processor, then you have a lot more options to map it, because it just spins to spins, and the number of swaps you have to do normally is already directly reduced, because it's really such an obvious mapping. But we can do this a little bit more mathematically. Here I just show an example where we did actually do a calculation of an NMR spectrum on an actual quantum computer. Mind you, this is a tiny example. It's just two spins, but it was done through cloud computing on Bracket using an ion trap quantum computer. And now what did we calculate here? What you actually need to calculate is the following object that I showed there on the right, where you have basically some prefactors, and you initialize your qubits in basically a kind of arbitrary state, when you just initialize them again and again, in some kind of random state n. So you just initialize your qubits up and down. It reduces a little bit how many states you need. And then you time evolve under a spin Hamiltonian, and then you measure what comes out. So that's it. You do this again and again, and then get an average of this object. And then these prefactors are trivially calculated from kind of your initial and final state. This is just the magnetization of the states. So it's just basically your qubit is up or down times some prefactor. And I will discuss in a second where we get this Hamiltonian from, because actually that is a huge amount of work. But let's say if we have it, It's just a standard, kind of well understood spin Hamiltonian. We just do a shorter time expansion. Of course, if you have other clever methods to do this time evolution, it's also good. A lot of people work on this. So it's a relatively clearly defined problem, and it is, the most standard type of problem where we believe that quantum advantage is possible. The time evolution under a spin Hamiltonian. Yeah, it doesn't get, let's say, much more obvious that we believe that fundamentally quantum advantage should be possible, but doing a time evolution under a spin Hamiltonian. So this work is discussed in this paper here, if you want to look it up. However, I also want to emphasize the question of achieving quantum advantage in principle gets kind of even stronger. I want to emphasize here, if you calculate this object here, you don't go through all n and m, because the number n and m is exponential. In fact, what you do is you sample. Yeah, and you can show that a polynomial number of samples gives you sufficient precision. So you sample this solution. So it's in fact not only a quantum simulation problem under a spin Hamiltonian, it's also a sampling problem. And we also know that quantum computers should be pretty optimal for sampling. Yeah? Since for all the problems where quantum computers have achieved quantum advantage, we're abstract sampling. It's not real ones, but this is a real one. So this looks pretty optimal, and you can also note this, the fact that this is sampling problems, you see this when you look at the exact classical solution. A numerically exact solution scales actually not like 2 to the n, with n being the numbers of spin, but it scales like 2 to the 2n. Yeah? Because your classical solver also has to take both sums n and m. Meaning it has to sum over both exponentially large sums, and then you have a 2 to the 2n scaling. Meaning already with 30 spins, your classical solver is not going to be exact anymore. Yeah? So directly you compare to something where you sample the quantum computer and do some approximation, versus something where also your classical solver needs to be approximate. So there's no way to make a classical solver that is numerically exact at 30 spins. And I think that's also completely uncontroversial to say. Yeah? I mean, as far as I know, the best numerically exact solution for this type of spin problems was done for 22 spins. And this was like really high-end, high-performance computing and everything. And the 22 spins with exact solutions is over. And I emphasize this exact for a good reason that I will show you, because you can actually make very powerful classical approximations. Yeah? So we will see this in a second. But so right out of the gate, if we look at this problem from an abstract perspective, it is the most quantum advantage looking that is imaginable while still being an industry problem. And now let me discuss how we get this Hamiltonian. So that's a quite important part of our work. This is the Hamiltonian we want. And here I write actually the spin. So you could also write here sigma j. I write it I, because in nuclear physics, people write the spin not S, not sigma, they write it with I, so that's the notation that people use generally, so we choose this notation here as well. But so what you want is, you want to say, okay, this is my molecule, and I, for example, define it like up here, yeah, in the picture. And this, I give you this picture. And then I need to get out somehow this spin Hamiltonian, and then I need to do the steps I showed before, for example, on the quantum computer or classically to get this spectrum. And what you need here are these chemical shifts. This is what I discussed before. So each of these nuclear spins gets shifted from the electronic structure, yeah, of kind of all the atoms, all the electrons that are kind of around it. And then, of course, these spins are coupled also. This is actually a coupling that is not directly your kind of magnetic coupling, but this is also through the electronic structure. So this you need to calculate. And so how does this kind of workflow look like if you want to do it? So first you need to start with a really quick method that goes from, like, you put in the 2D structure and get out 3D. Then you need to do conformer sampling, meaning all these molecules kind of vibrate a little bit. Then refine the final structures you have even further with like better methods. And then you can kind of extract these NMR parameters. And let me kind of show you like how this first step looks like. I mean, again, an actual user in that space would want to define your molecule either using this picture or what's known as smile string. So this is a kind of unique way to write down all types of molecules, and can also be quite convenient. And then you get out your 3D structure, or you need a way to get like an initial structure that is not complete nonsense. And then, of course, you could start with that structure and go through this. This is done all classically, by the way, here, just to see how this goes. And calculate the spectrum. And you see here our calculated spectrum is terrible. And this is, of course, because we did not do the other steps. So it's really quite important to do this conformer sampling. For this type of molecules, it's these rotomers, the fact that these groups rotate. And the NMR experiment is actually relatively slow, meaning the result will be an average result over these rotations. So when you produce these parameters, you also have to kind of average over this. And yeah, you have to build like a workflow that does this quite smoothly and reliably, and that is non-trivial. And here are some examples just to show people that we can actually do it. For a couple of molecules where we get very good agreement between simulation and experiments. And you might remember, initially I focused on this point and emphasized that this transformation to quantum is an important step. And I say this because actually at HQS, the majority work on this topic goes into this step, not on the quantum computing side right now. Yeah, so this getting precision in here, in this step to get to the parameters, eats up the majority of time right now. And it makes kind of sense, you know, if the precision is not there in this step, I don't need to continue, yeah? I mean, then I've already lost. So this needs to be really good. And now the second point that I emphasized, which makes a lot of sense and needs to be done if you want to make sure. So what I told you before is that's an amazing problem that, you know, in an obvious way, completely self-evident, it can achieve quantum advantage. Is that true in a practical sense? Yeah? And to find that out, it can be, you know, necessary to write also an absolutely optimized solver for the same type of problem. Optimized means also that it uses the best possible approximations that are classically available. Yeah? And I can show you an example. So this is a measured spectrum for a molecule called Fridolin. I show you this molecule because it has quite a few spins, but not an infinite amount of spins, so just perfect, yeah? Just 50 spins. 50 spins. Looks pretty cool if you want to map something to a quantum computer and would want to achieve quantum advantage. 50 spins would need 50 qubits. Looks pretty feasible, but looks also already, say, superficially, so that you should not be able to solve it classically. It's definitely the case that you cannot solve 50 spins numerically exactly. So you definitely will need approximations. And this spectrum here was measured at a frequency, I mean, it says here frequency 80 megahertz. Actually, this means that the magnetic field in this NMR device was low. This is so-called low-field NMR. This was also then a device that is not as huge as the one I showed you before. This large devices are 400 megahertz devices. So this is a small benchtop device at 80 megahertz. And the reason for this is, the idea at least, you know, if you push these peaks closer together by making the magnetic field lower, that then maybe it also becomes a harder problem for a classical simulator. If you have more degeneracy in all the spin parameters, maybe it becomes a harder problem. Also, it's like this is one side, of course, but of course on the practical side, what is in it for the people in industry? People start using these 80 megahertz devices because they are cheap. So people would really like to switch to 80 megahertz, and it's like a really upcoming topic. And what you also see here is now the peaks are broader. This in some sense is they don't need to get broader by going to smaller number of megahertz, but because you kind of scale your axis here differently. You move it all together, so the peaks have kind of the same width to some extent, but because you squeeze it all closer together, it looks broad. And I would also say the measurement could be better, I was told. So the width here is about 1 hertz width, and you could actually go down to maybe 0.2 hertz. So we could probably still improve this by a factor of 5 in width. Now, 50 spins looks good, but there was another reason why we wanted to have that particular molecule. It's because it's relatively stiff. So there are not that many conformers and rotamers, keeping it a little bit this kind of work of getting the classical parameters under control. So we are able to actually get all the spin parameters for this. And now I already show you right out of the gate. I will wait, I'll explain you now. How do we do a classical solution for this? I mean, what is the way? So the obvious point is this: you have a hydrogen atom somewhere where you have your nuclear spin, and this nuclear spin generates a certain magnetic field that you measure. And the question is, okay, does this spin really see the other spin of the other hydrogen far away? Yeah? And the answer, of course, is no. Or, I mean, probably not. Yeah? So what you can do is then you can start to use clusterization methods. That is at least from the idea that's well established, where you don't always solve the whole thing, but you cluster it in smaller sub-parts. And then your problem only scales exponentially within the cluster. But then you keep this cluster size at a reasonable size and see if everything converges. And doing this in practice, that this really works, especially without you fine-tuning everything, can be quite difficult. But I think for everyone here, conceptually, it's probably clear that this is fundamentally possible and a good idea as an approximation method. So this is the way you do clusterization. And right out the gate, I show you that we simulated it, but I'll argue in a second why we know that this solution actually is a good one, why it's reasonable. We do some fine-tuning here. For example, our spin parameters should be good, but we still fine-tune it a little bit by, for example, shifting the whole axis by observing a little bit how it fits and doing some other small tweaks. But now, how do we know that our classical, that if there are still some deviations between our calculated and measured spectrum, how do we know that it's not because of the quantum mechanics of the spin problem? We do it like this: we choose this cluster size and just increase the size. So we go from small cluster to a large cluster. And the upper calculated result up here, as you see, we have 4 cluster sizes shown here. So you would expect to see 4 lines. And maybe if you're good eyes, you see it like there's a little bit of a gray line up there. But what you see is already at the smaller size, it has really converged quite a bit. And the reason here is probably this broad line width. So if you have really broad line width, the features you need to resolve of all interactions of all spins also is less. So for obvious reason then, cluster sizes also stay small, things converge very nicely, and we get also quite good comparison between our calculated result and our experimental result. And what you need is basically either better line width, so kind of more features, or you need stronger couplings between your kind of nuclear spins. However, let me also point out, so here we could solve it, but we know that cases exist where you have really strong couplings between all the hydrogens. Here is a molecule, a diphosphane molecule. So phosphanes are quite important, for example, in the production of fertilizer. And this molecule is also, of course, particularly famous as a benchmark for NMR solvers, because actually all the spins are very strongly coupled. So these two phosphanes really strongly couple all the hydrogen atoms in the all the spins from all the hydrogen atoms in the problem here. And then for this case, really spin-dependent clustering fails. And we could still solve it classically, but just barely. Yeah, I mean, this with 22 spins, this is at the absolute edge of what's solvable. As I said before, by the way, I mean, 22 spins is the numerically exact solution at its maximum. And for us, it was only possible to solve it without using high-performance computing or anything, because of some symmetries where you could reduce the state space further. And with this, I'm at the end. And yeah, I want to say basically, I think I want to emphasize this structure, which I used to go through the case, this kind of use cases. I want to emphasize that transform to quantum can be quite useful because, or thinking about this, because it can also enhance the type of problems that you can shove into the quantum computer if you think more about this. And you can shove towards really provable quantum algorithms. So your original quantum algorithm might, for example, look very abstract, like solving a spin problem. How was that good for? But by putting work into the transform to quantum, you can put problems here. And similarly, you might say the optimal polynomial dissection problems looks really useless. But it's not clear that it's true. Yeah? If you put in work in here, it could be possible to find really cool cases that fit. And of course, working here also gives you a good way of later benchmarking, getting a feeling of what's necessary, and also has the advantage of producing values right now. And I also showed our use case here to give people a little bit of a feeling that even for cases where on paper it is the absolute most optimal quantum advantage use case, classical solvers can be extremely powerful. And that is why I'm often a little bit skeptical if you start from something where you don't have a super strong argument quantum advantage on the quantum computer. Yeah? So if we see this, I feel what this indicates is you need a really strong reasoning for why the quantum computer can be vastly better. And I think if it's there, yes, classical solvers are competitive, but sooner or later we will find really cool cases where the quantum computer will do solve relevant problems. Thanks.
Thank you so much for your presentation. Now it's time for questions from the audience.
I have several, but maybe I'll start with the optimization one. You did mention that there is one provable scaling behavior for one algorithm with respect to optimization, and that's like very short all the scaling behavior of different optimization. So you did not name this algorithm, which scales as 1.7.
It doesn't have this. It doesn't have this. It didn't give it a name.
Okay. So
it's a combination. It's basically, but it's a combination of calling Grover in a very clever way many times. So it's basically Grover-based, I would say. Yeah. But it's put together in a really complicated way of when you call Grover, how. So they use some base algorithm that is like the minimization algorithm that is Grover-based, and some classical ideas that put it all together. But yeah, so the base of it is Grover. Yeah?
yeah.
I mean, it's quantitative for experimental time dynamic programming, and they basically use ideas from time dynamic programming, which I'm personally not super familiar with, and put in Grover in some way, but it's pretty non-trivial.
I have a couple of questions.
Sure.
One is, when you double the cluster size, you rarely saw any improvement.
Yeah, sure.
And what is the computation resource requirement that increased from like 7 to 14?
Oh, it's exponential. In cluster size, you're exponential, meaning that's pretty brutal. 14 cluster size is like at the edge of cluster sizes that we do. Maybe we go to 16, but at 16 cluster size at the end of what's possible. I mean, of course you could push it, but let's say practically possible. Yeah?
The next question is like, if we can cluster it and do this in quantum way, but how about classical way? Like we can still cluster.
No, I mean, yeah, no. This when I talk about clustering, you could also put these clusters on the quantum computer if you want. But this clustering is all I showed here for this clustering was classical. All the rest is for classical because this is a great method to do it classically. That's why it's also limited. This exponential scaling is for the classical solution. Your quantum computer would not scale exponentially in the cluster size. It would scale linear, probably. Yeah? So the quantum computer has an advantage, but if your cluster size has converged, once you have converged, and maybe that is small, from that point onward, your scaling is linear. Yeah? So once your cluster has observed, okay, you have a bad prefactor if you want, but I mean, the classical computer can handle it. There's also lots of ways to trivially parallelize your clusters. So I mean, you have a really brutal way to speed this up if you want.
So thanks, Michael, for the nice talk. I have several questions on the Hamiltonian view of the NMR. So you actually said that this is a very tough thing to do, right? So, so first, you talked already about the rotor mass, so the dynamical degrees of freedom.
Mm-hmm.
So how would they add? So here,
for example, let's take this thing. Yeah, what you do is you actually calculate the rotor mass, and at the very end of doing all this conformal mass and all, you produce an average structure, and then you take this average structure and then calculate the Hamiltonian. Now, for all details, I would have to ask our quantum chemists, to be honest, because they do it.
Because I mean, the distance should also then enter in the JIJ. So
This is the thing. It's not so if you have, let's say you have a JIJ that changes in time, for example, maybe semi-randomly, but this change is much faster than your experimental measurement time. It turns out that your final Hamiltonian contains the average J. To be honest, that is not, it's known as motional averaging. It's a really famous effect. And I think it's also famous because it's not trivial. So because when I looked at this first, I thought, oh, we need to keep all the JIJ for every conformal and everything. And then keep it noisy and everything. It's going to be super fun. But no, actually, it averages out and you have only one JIJ, yeah, the averaged one. And that is super important. The reason why NMR works is because of this motional averaging. Yeah, because there's a lot of terms, for example, the direct dipolar terms in the Hamiltonian, I threw them away. Why? Because of the motional averaging. So that's super cool and super important and makes NMR actually very useful, that you have this averaging.
okay, and the I, so sum over ij, also on the quantum side,
Yeah,
with the same arguments of the clustering, it shouldn't be necessary to take the full sum, right?
it's true. It's true.
How
But
are you solving this?
the cluster, well, I mean, look, you can do a cluster ring here. For example, let's say you would have a protein and it has like 2,000 spins. But it turns out, for whatever reason, the cluster size you need to take would be 50 spins. Perfect. And you say, okay, now I cluster it in 50 spins and solve each of these 50 spins clusters on the quantum computer. Yeah? Because I cannot do 50 spins classically as cluster. And great, we have found a really amazing problem for the quantum computer. So, so in some sense, clustering classically or quantum, it doesn't really matter. It's just if your cluster stays so small, you don't need a big cluster. You just do classical. Yeah? you need to find a problem where your cluster needs to be.
So the sum needs to be sufficiently large such that you
Exactly.
cannot.
Exactly.
And the last question would, can you emphasize what's the role of delta I here?
Yeah, this one. I mean,
Yeah.
this.
So
Yeah, so the delta I comes from in some sense, the magnetic effect of, so you have the magnetism of the spin, and then all your electrons also create like a countermagnetic field. But this depends on the electron density. Yeah, this is how NMR, basically this delta I depends on what is the group to which this H is attached. Yeah? Normally in NMR you basically only look at this delta I's and nothing else. And they are, that's why you make the magnetic field big, such that, you know, this delta I, the effect from this delta I's is much bigger than the J. Then you have tabulated all your delta I's, and then you just go through and see, okay, a delta I like this indicates a chemical group that looks like this. Delta I like this, chemical group this, and so on. Yeah? And then you put it together. So this is kind of how this delta I comes about and what it's for.
So it's the background magnetic field from the molecule.
Exactly.
In the end, the problem of solving the NMR Hamiltonian is quite similar to the electronic structure one. So if you have like weak interactions, we are totally fine with the classical methods, but if there are like strong interactions, like the active space method.
This is a fair question, but the key point here is that generally you would believe that getting good parameters for organic molecules should be possible with DFT. Yeah? Because organic molecules in basically a ground state, electronic ground state, should be solvable with DFT. From this does not directly follow that the dynamics of the resulting spin problem needs to be easy to solve classically. Okay, I mean, you know, maybe at some point we will notice that it's always that way. Yeah, but I would say at present there's no indication that there's a kind of in any form a direct, because, you know, one is dynamical, yeah, the other is static ground state, and so on. I mean, this could be true, that weak interactions that allow you to do DFT also create, in the end, always a spin problem that is classically easy solvable. But I would say it's not the case that we would expect it right now.
That was not my point. It's more like relating to, okay, like an electronic structure, we have these big molecules, and often you can get away with DFT, you have like only interactions, but there are some parts that are strongly correlated, so we do need to sort of use maybe the quantum computer or like this.
Yeah, oh,
Here,
this is, yes.
Here looks very similar, right?
This is true.
We have like a lot of area that's quite easy solvable, and maybe there are some areas that need like the full...
In that sense, you're completely correct that the clustering is the spin dynamics version of the active space, where often the active space can actually remain pretty small, and the cluster here can be. In that sense, yes, this is exactly super similar. I mean, this type of clustering method we use everywhere in quantum mechanics, and they often work.
In the end, for finding industrial relevant use cases, it's for both, we need to find problems where we have big, strongly correlated problems that are still industrial relevant.
This is true, but the NMR problem is better defined than saying I do complete active space calculations. Yeah. So as a sub problem which you put in the quantum computer, I can just work on the quantum computer. So it's better defined also in terms of how we found it easy. You know, there are people in industry that stand at the device and they would like to have a really good software to connect what they see to what is in it. Yeah? So that it has also a more smoother, direct explainability what it would do. So it's actually a bit of a better use case in some sense. And it's dynamic, making it also better for the quantum computer. Also, you could do spectroscopy also in electronic structure. Then it becomes again similar. And if you look at currently existing gate counts for error-corrected quantum computers, actually the gate counts for full quantum chemistry are pretty sad. Yeah? And for spin problems, right out of the gate looks good. I mean, that's doable. I mean, just formally, I can write down your spin Hamiltonian where you can achieve quantum advantage, or should achieve it with the error correct calculation, no problem. Yeah? While for quantum chemistry, the full quantum chemistry Hamiltonian with the 4 index terms.
Yeah, this one is only quadratically scaling while
Exactly.
the electronic one is
Exactly.
So you've shown an example where the cluster size converged
Yeah.
below 10, I would say,
Yeah.
and you said that 16 is maybe the limit where which you can solve classically. So what are typical cluster sizes in molecules that are maybe relevant?
Yeah, so far, let's say if you don't take cases like if you don't take cases like this, the diphosphane, in our database, we have been able to converge everything below 14 or 16, but our database currently has about 100 molecules, and will be filled with another 3,000 soon, as soon as possible, let's say. And then we will see how much gets preserved. And there are a couple of things that we are still checking around in terms of discretion, and that is what is a reasonable line width. Because, I mean, the conversions come from lifting the degeneracy through making a big delta I, big magnetic field, and line width. These two things generate the convergence. And we have seen, let's say, for some cases, if you make low line width, we do not get convergence at a size of 14. Yeah? Also for, like, say, standard cases. And we just have to play a little bit around, are these reasonable line width that we put in? I mean, it's not pathological. Yeah? But let's say, for very standard cases, with standard line width, so far we get everything to converge to about 10.
Yeah, on this slide, you said that the symmetry enables exact solution of that molecule. But so symmetry is also, if you have on a quantum computer, it's also relevant. And it's
Sure.
How do you see the quantum advantage in that kind of light?
I mean, the Hilbert space, you know, I mean, we're talking, you reduce the Hilbert space from 2 to the 44, yeah, which is the full Hilbert space, to 2 to the 20. Yeah. I mean, symmetry is actually reduce it such that you can barely squeeze it still on a classical computer, but always by a factor of 2 or whatever. You know, so it's minor improvements, but minor improvements that made it possible to solve this problem, because we could not have done 2 to the 44 scaling problem. Fundamentally, it's possible, but we don't have the resources. So I don't know. I mean, it's maybe the symmetry question doesn't worry me. It's more the fundamental question that say, are cases? Is nature just made the way that in fact it's not quantum mechanical and all practical things we see are actually classical? Is it maybe that way? That the things that arrive as a physical effect in the macroscopic world that we see turn out to be pretty classical often. And for reasons that make sense, because they are the stable part. And this is maybe more what we have to look at. Is it maybe so that, I mean, quantum chemists will tell you that they feel they will solve every actually relevant chemical problem classically efficiently. Because of course their experience is that they have improved methods consistently over 40, 50 years. And so, you know, we have to see if this gut feeling that you get from chemists is correct or not. And I would say, I think there's a still good chance that the quantum computer will do it, but this is more the big thing to look at.
Thank you so much to the audience and to Dr. Marthaler. And so this is our time for today. We hope you enjoyed it, and we'll come back on the 10th of July with Dr. Achim Kent from the University of Waterloo, who is talking about his work. So have a good day and see you in the next one.